Hello, everybody. Thank you for coming to the February Center for Climate Science and Engineering event. So my name is Jamie Fine. I am the manager of the CSE, and today we have a very good guest lecture from Marc Couture. He is from U of T, and he's going to be speaking to us. But before we get there, we have a few opening remarks because that's how webinars go. So for those who it's their first time coming to one of these events, the CSE, it stands for the Center for Climate Science and Engineering. It's a research and education center within the Civil Engineering Department at U of T. It was established in 2019, and it's made up of a multidisciplinary team of faculty members. So shown on this slide, you should be able to see now. So there are 7 faculty members. Oya Mirkan, she is the center director. She focuses on structural analysis. Marianne Hatzapalu, she focuses on transportation engineering. Paul Kushner focuses on climate dynamics. Graham Norvell focuses on health and process safety. Daniel Posen focuses on life cycle assessment. Karen Smith focuses on atmospheric physics, and Marianne Tucci focuses on building science. So as you can see, there's a really multidisciplinary group of faculty members that work as part of the CSE because tackling this, the intersection between engineering and climate change really does require this multidisciplinary team because of all these the interactions between all these urban infrastructure components. And then the bottom right corner is me, and I'm the CSE manager. So the next, some other housekeeping. So the next lecture that we have coming up is on March 24th, and it's going to be presented by King Tung. And the topic is going to be looking at Enwave, so the district energy provider in Toronto, and looking at community energy projects that they're starting to look into. And if you want to find out more about these events, please visit us online at uftcse.ca. You can get on our mailing list if you're not already on it, and I encourage you to do so. And then I think we're going to have 2 more lectures after this one, but they are still in the planning process. So look forward to more lectures. So, and as I mentioned before, in addition to us being a research center, we're also an educational center. We have a free workshop series that's for U of T students currently. We're hoping to expand it to be more publicly available. And the next one we had, so the one we had in February focused on building science topics, which really will relate, I think, to what Marc is going to talk to us about today. But the next 3 we have coming up is in March, we have energy systems. April, we're talking about GHG emissions in transportation. And then in May, we're talking about life cycle thinking and climate policy. So if you're part of that workshop, please do attend, and we look forward to seeing you there, in addition to coming to lectures, of course. And I think that's it for housekeeping. So the only thing left to do now is just to introduce our speaker. So our speaker today is Marc Couture. Marc is the Director of Sustainability and Energy Management at U of T. He's an expert at diagnosing complex energy ecosystems and developing, I think if you can hear my dog, I apologize for that. Marc is an expert at diagnosing complex energy ecosystems and developing transformational energy and sustainability retrofits. He focuses on reducing energy consumption and greenhouse gas emissions, simplifying operations and maintenance, renewing assets, and improving occupant wellness. He has 15+ years of expertise with roles such as sustainability co-chair, director of operations, energy manager, critical infrastructure and energy management project manager, higher education solution development, and HVAC solution engineers. As you can see, he really knows a lot about really getting into the design and operation of buildings to make them sustainable. And he's also currently serving as a key member of the International Society for Energy and Sustainability Research on the Knowledge Board. And I think that's all I have to say. Marc, did I miss anything with that?
That was fantastic, Jamie. Thank you very much.
Well, it was your bio I read, so really it was all you. Okay, let's get started. So everyone, please give it up for Marc. Yeah, give it up for Marc.
Thank you, thank you, thank you. I'm going to try and share my screen here. Can you guys see that okay?
Yes, I can see that.
Perfect. So I just have to find out where my PowerPoint went to on my screen. There we go. Got it. So firstly, I wanted to thank you, Jamie, for inviting me today. It's a pleasure to be here and to be speaking about some of the exciting stuff we're doing at the University of Toronto. There's been lots of change happening here, and yeah, I'm very excited to be able to present this to you guys. And you know, as Jamie said a few minutes ago, you know, if anyone has any questions or wants to add any comments or flavor to this, please don't feel like you're interrupting me. I'm going to try and stop at least 3 or 4 times throughout the presentation, sort of opening up some questions or some conversation and discussion. So you know, please feel free to raise your hand or to ask questions throughout the whole presentation here. And what we're going to be talking about today is sort of our climate neutral campus master plan at U of T, and how we went about the evaluation, planning, and strategy behind our climate commitment and our master plan. So on the agenda, we have our commitment to climate action, and we'll review some of the elements of our low carbon action plan over the next 5 years, which is, and then also get into sort of the longer term vision around our net zero campus master plan for towards 2050. We'll look at some project highlights, and then we'll sort of finish it off with talking about some of our partnerships and engagements through the Sustainability Office here. So to kick it off, I kind of thought I'd go through a little bit of context, give us a bit of sense of scale. So when we look at U of T at the tri-campus level, we educate more than 88,000 students, and that makes us the largest university in North America. We also employ more than 20,000 faculty and staff members, so our population you know, becomes more than 100,000 people at a tri-campus level. And you can sort of see here how that breaks down. But this sort of gives you an idea that, you know, we're actually like a city within a city. So we are, you know, the St. George campus at least is in downtown Toronto, with Scarborough campus being in eastern Toronto, and of course UTM being over in Mississauga. But you know, this does give us a very significant footprint within the city of Toronto. Just how significant, you might ask? Well, we have at U of T the dubious honor of being the 3rd largest GHG emitter among institutions within Ontario's broader public sector. So that is not, we kind of joke in Toronto that we have the bronze medal, but we're very happy to give that bronze medal to anyone else who wants to take it off of our hands. And we hope to actively get rid of that bronze medal through carbon reduction. So we are very eager to hand that off to someone else. When we look at our carbon footprint at the U of T, we start to compare that to others in the commercial sector or in the industrial sector in Ontario. We can sort of see how our emissions sort of stack up. So when you see, even compared to Toyota, GM, Ford, the airport, Honda, or Sanofi Pasteur, we're significantly higher than all of them. And in fact, our reduction target of 59,000 tons alone is larger than the total annual emissions of any other Ontario university. So it just sort of shows you the challenge we have in front of us here. So we are building on leadership in operational sustainability. The U of T has been awarded Canada's Greenest Employer 7 times. We currently have an $8.5 million green revolving fund, which is going to be boosted, I believe, to over $10 million in 2021. We are, working with a district energy system that's over 100 years old, and we do produce more than 80% of our heating and 20% of our electricity needs for our downtown campus here at St. George. And since 2011, if we want to recap just quickly, we've achieved a reduction of more than 55,000 tons of GHG emissions. We've saved over 1.25 billion liters of water, equivalent to 500 Olympic-sized pools. We've also avoided over $30 million in utility costs. Today, we are very fortunate to have some very bold leadership. I'm going to read through this quickly because I think that it's very important. This is a message from our Chief Operating Officer, Ron Saporta. And he says, the launch and implementation of our energy and carbon master plan is our first step towards becoming a climate positive campus. To me, this means not only reducing the operating emissions under our control, but also mitigating additional carbon emissions to achieve net negative emissions. This plan is transformative beyond the infrastructure that will enable carbon reductions across our campus. It will also set a new precedent for how we upgrade and optimize buildings and infrastructure to be carbon neutral or better. Highlighted are some of Canada's most ambitious low carbon projects in our historic core of campus. If we can demonstrate these possibilities here, it speaks to what can be done to aged infrastructure and old buildings everywhere, now and with future generations. I really like that quote because it sort of shows how ambitious we are and how committed our leadership is to reducing our carbon emissions at U of T. Now, if we look just quickly here how our emissions at the tri-campus level break down, we have 83% of our GHG emissions that are at the St. George campus, with 8% and 9% respectively at Scarborough and Mississauga. This sort of gives you a bit of history. This dates back to 2019, but it's substantially the same today in the start of 2020. At a tri-campus level, we're roughly at somewhere around 114,000 metric tons annually. By 2024, with our low carbon action plan, we're looking to reduce that down to around 82,000 metric tons. Our 2030 goal is a minimum of 73,000 tons. Ideally, we'd like to be substantially lower than that. And our commitment by 2050, we're looking at trying to achieve 80% absolute reduction in on-site emissions and achieve the balance of 20+% through offsite renewables. But these will be U of T owned assets, and we're hoping for some virtual net metering. So this gives you an idea of our carbon intensity at the St. George campus. So right now we have sort of an average of 69 kilograms of CO2 equivalent per square meter as an annual average. If we want to achieve our targets, we actually need to get down below 9 kilograms. So it's just a graphic that shows the representative sort of decrease we need on our St. George campus. So how do we plan to achieve our goal? Our low carbon action plan, which we're going to start with, sort of takes a three-pronged approach. First being the production of energy, the distribution of energy, and also finally the consumption of energy. So this is a fun graphic that I really like because I think it speaks volumes. I call it the energy pyramid. The energy pyramid sort of plays a key role in developing the strategic hierarchy for how you look at energy master planning. So at the top here you have energy source, and this is your input fuels. So it could be oil, biofuels, gas, electricity, wind, or solar. And at this level of the pyramid, you're really affecting your long-term strategy, and this is going to have a direct impact on your sustainability. When you go down to the next level of the pyramid, you look at energy procurement. These are things like it can impact demand response, the net metering, load shifting, energy storage, time of use, sort of how you're buying energy, how you're delivering energy to your buildings or to your campus. And here you can start to look at things like different rates and tariffs. You can look at breaking up rates and costs, and if you have the latitude to do so, to leverage some of these to be more favorable and drive more value. The next level is energy efficiency. We look at here sort of at a utility scale or at a district scale, sort of thermal equipment, energy distribution, and you're sort of looking at efficiencies also from how you're producing, like from chillers, boilers, or heat pumps. And then finally, at the base of the pyramid, you have your energy consumption. This is everything within a building, sort of your demand side. That can be lights, plug loads, ventilation, pumps, equipment, and also basically anything that's end use. So our carbon reduction framework, when we're looking at this, we're definitely taking a conservation first approach. This is an automatic first step. There's a lot that can be done here, and this includes some simple measures, things such as temperature setbacks. As a general rule of thumb for our climate and the age of our buildings on our campus at least, for each 1 degree C of temperature that you reduce on your thermostat setting, you can actually save 3% of your energy. And this is roughly true for both heating and cooling. So you can imagine if you can change your set points in your thermostats by 3 or 4 degrees, you can start saving now 12 to 15% on your energy bill just through changing set points. So anything that we can do from a conservation first approach, as it says here, the cleanest and cheapest energy is the energy we do not consume. So measures that we're looking at here are sort of campus-wide retro commissioning, continuous commissioning, looking at things like steam traps that might be leaking and really consume energy for no reason. There's no value in a leaky steam trap, broken equipment, anything like that. So we're taking an aggressive look campus-wide at retro commissioning and continuous commissioning. Another thing that is going to play a significant role moving forward for us is we just released in 2020 a revised energy standard at U of T. And I'll talk a little bit more about this later, but we're essentially mimicking the Toronto Green Standard and trying to also raise the bar a little bit for ourselves to require that every minor renovation, major renovation, or new construction on our campus meets strict performance standards in terms of energy use intensity, as well as greenhouse gas intensity and other components as well. But this will have a big part in trying to reduce the consumption for our existing buildings. To give you an example, within this standard, if we're doing a major renovation for HVAC equipment, this standard will require for like a lab building per se to reduce the energy use intensity of that building by 43%. So that is sort of a strict standard that we have internally, and we've already started to launch projects that will be compliant with this new standard that took effect back in July. So if we're looking at, I'm going back to the energy pyramid here quickly. So when we're looking at energy consumption and we're looking at demand side, essentially what we're trying to do, if you want to picture it, is we're trying to reduce the size of the base of the pyramid. And if you reduce the size of the base, everything above it must also follow. So I think that's a good visual here. So we're trying to essentially, with the consumption piece, we're trying to reduce the width of the base of that pyramid. One of the big sort of programs that we just launched here to really tackle the energy use intensity of our existing buildings is a deep energy retrofit program. So right now, the energy use intensity of our St. George campus is roughly 1.68 gigajoules per square meter. And what we're trying to do from now to 2050 is implement a program targeted at reducing the energy use intensity down from 1.68 down to below 0.7 gigajoules per square meter. To give you, if you're not familiar with that scale or those terms, to give you a bit of a better sense, a net zero energy building would probably be in the range of somewhere 0.25 gigajoules per square meter. So we can't quite get to 0.25, I don't think just yet, but we are going to aim to get that as low as we possibly can with the technology we have available to us. And with existing buildings that are, many of them over 100 years old, I think the average age on our campus is probably over 80 years old. Given the age of the buildings and the renewal cycles, we're trying to significantly reduce that energy use intensity. Through our deep energy retrofit program, that's sort of defined for us as being greater than 40% EUI reduction with a deep energy retrofit. And what we're trying to do here strategically is to affect transformational change in these buildings through electrification of our heating systems by converting our buildings one by one from steam or from high temperature hot water down to low temperature hot water, and also to identify and minimize the losses in the operations of these buildings. Losses in terms of heat or energy. I think that one of the biggest impacts we can have on our GHG emissions as part of these deep energy retrofits is to minimize heat losses. So heat losses through radiant heat losses, through convective heat losses, or also through conductive heat losses. So as we're going and doing these deep energy retrofits, we're really trying to essentially cut the emissions in half and the energy in half. This graph here is nice. It sort of shows some of the benefits of deep energy retrofits, both the monetary benefits in the bottom, but as well as the non-monetary benefits on top. So as we're looking at doing these deep energy retrofits, we're paying close attention to increasing the resiliency of our campus and our buildings. We're looking at avoiding some of the costs associated with new district energy infrastructure that we'll have to be building out for new buildings or for part of our carbon neutral master plan. We're also putting the health and well-being of our occupants as a top priority. We're looking at optimizing lighting levels, noise levels, temperature, humidity, air quality, and putting that front row and center. And of course, here we have reducing the carbon emissions. So it's not just about saving energy and saving dollars, it's really about creating a better environment. Going back to the energy pyramid, when we look at the deep energy retrofit program, that's really holistic in nature, where your retro commissioning and your continuous commissioning really sort of looks essentially at energy consumption at the base here. The retrofit program, the way we have it structured here, is to really be holistic. And we have sort of a process that we're looking at there. And first, what we typically do is we perform an energy cost analysis, as well as a GHG intensity analysis. So we look at all the different fuels that are available to us, and we look at the different costs, the different rates. We look at different strategies that we can maybe use for procurement or for demand side management, and see how that impacts rates and tariffs. And we see what best aligns with our long-term strategy and our sustainability goals. And then we try and retrofit the building systems to try and meet those targets and to try and reduce the EUI as much as we possibly can. So the other piece that we're looking at here in some of the non-conventional ways to look at deep energy retrofits is we're looking to drive the greatest value we can to the University of Toronto. And we're looking at this sort of from not just a triple bottom line, where you're typically looking at people, planet, profit, but we're also including a fourth P in there, and that fourth P is purpose. And for us, that's really supporting our core educational and research mission. So anything we can do as part of this transformational change, part of these deep energy retrofits, to support community engaged learning, to support the campus as a living lab, to promote experiential learning, and to tie to the existing research activities and assist with commercialization of new technologies being developed at the U of T. We are actively looking for opportunities to integrate this into our retrofits and to our campus infrastructure projects as much as we can. So this sort of leads us to trying to foster innovative solutions. So by working with students and faculty, we're trying to foster these partnerships with academics and try and look for ways and solutions to reduce carbon emissions, but also look at developing external partnerships. The campus as a living lab, I think, is a really great opportunity. We've been submitting projects through the Sustainability Office to this program for the last few years, and it really gets students working on real-life problems that can be directly applied to our campus and to the work that we're trying to do here to green our campus. So we've worked with many different multidisciplinary capstone projects. We've looked at living lab projects, both independent as well as in course, and we feel this provides great value. This one here is a carbon capture technology. So we've been working with the CERT team, which is Carbon Electrocatalytic Recycling Toronto. They are participants in the Carbon X Prize, which I believe the competition period just wrapped up. It was taking place in Calgary, and the CERT team is just doing their homecoming back to Toronto early this year. And they've gone from lab scale to a prototype to a pilot project, which was part of the competition in Calgary. And their technology is able to convert CO2 into valuable ethylene, ethanol, and syngas feedstocks. And what we're hoping to do as they continue to develop their technology is to integrate this into one of the technologies we use to achieve our greenhouse gas reduction targets on campus. So we're looking to find a home for them on campus where they can convert some of the existing emissions that we're generating on campus into a valuable feedstock. We're also working with our Department of Forestry, working with experts and students and community partners here to look at active forest management and how that can also reduce our carbon emissions. So we estimate here as part of our low carbon action plan that we can reduce close to 1,100 tons per year. Here we're looking at a sustainable lab stewardship program. We've also got an edible campus stewardship program where I'm very interested actually and excited about our potential biodigester to go from waste to energy. We want to integrate that with our campus district energy system, and also looking at a zero waste campus. So as we look a little bit more into our carbon reduction framework, what we're trying to do here is to really first mitigate the impacts of climate change and also provide some resiliency as we adapt and we plan for a changing climate. Increasing the efficiency, of course, is a great thing, as we talked about in the energy pyramid. We're also strategically looking to electrify the heating, hopefully with heat pumps and other highly efficient technologies, and also increase the thermal resilience of our buildings on campus. This can be done through lots of different mechanisms. It can be done through increasing the air tightness of the building, increasing the insulation, providing more thermal massing, or even thermal energy storage, which I'll talk about a little bit more later on. As we look at deep retrofits in the buildings, I just want to sort of note here that the buildings in Toronto account for 50% of our GHG emissions as a city. Both the city and the university recognize that the deep energy retrofits are key to reducing urban emissions and also mitigating impacts on climate change. So in face of extreme climate, deep energy retrofits can increase occupant safety, health, and comfort. So most of what we discussed has been on the building side of the equation, on the demand side. Now I want to look more at the important strategic role at the top of the pyramid here. Look at sort of the fuel and the rates. So although we look at this on a building by building basis, most of our buildings at St. George here are connected to our district energy system. So there isn't a lot of options there for flexibility, because our intention here is to grow our district system and to keep our buildings connected to our district system. But now, as we look more strategically and more whole campus, we can look at our district energy system and try and see how we can transform that network to meet our climate goals. And of course, any changes you make at this point in the pyramid, will have a cascading effect and affect everything below it. So this is where you can really affect change, I would say, the quickest. This is, you know what, I'm actually going to pause here. Does anybody, I haven't been monitoring the chat, but does anybody have any questions or anything they want to talk about from what we've covered so far? I'll take that as a no.
Yeah, there's no comments in the chat that I can see, Marc.
How about your end, Jamie? Is there anything that you wanted to add in at this point?
No, not really to add in, but I guess it's really important just to understand that it's not just about designing new buildings that are nice and energy efficient. It's making, you can't just go and destroy all the buildings that are old, and you need to find ways to make them meet the energy goals. So it's interesting to see how that's being considered at U of T.
Yeah, absolutely. Existing buildings are a big part of the equation, and that's the trickiest and most difficult thing to do, is to convert old, inefficient buildings into something that's going to be climate friendly. Speaking of challenges, this is one of the biggest challenges that's sort of facing us, is trying to balance carbon with cost.
Yeah, Marc, there are two questions in the chat though right now. One,
oh great,
asking, will the slides be available after the presentation?
I can make the slides available, I believe, yes.
Yeah, and we are recording it. Marc, we'll talk about that after. And then another question is, how do you do deep energy retrofit in the large energy consuming buildings, those with lots of fume hoods?
That's a very good question. So buildings with lots of fume hoods, all of our lab buildings are definitely our largest consumers on campus. So as we roll out our deep energy retrofit program, we're kind of starting from the top down. We're looking at the largest consumers on campus and looking to retrofit them first. So these, out of our top 20 or so buildings, I would say probably 17 of them are lab buildings, so buildings that have things like fume hoods. So first and foremost, like I said, we're trying to increase the indoor environmental quality, so the working environment for staff and students. So we have to create a set of standards, especially for labs, around what kind of indoor environmental quality we're aiming for, and then try and optimize around that. So that being sort of a core programmatic requirement. We're looking at fume hoods that, if we're using existing fume hoods and it isn't an option to change them, then we have to try and calibrate the existing fume hoods to the right air changes, the right phase velocities, and make them as efficient as we can. And to make sure that the buildings are being properly ventilated and we have excellent indoor air quality for our occupants. After that, we try and mitigate the losses. So, fume hoods, they evacuate a lot of heat, unfortunately. So we look at techniques for recovering that heat and for also generating the heat that's required to heat the building in the most efficient way possible. Labs, the one good thing about labs is that typically they have year-round cooling requirements, and we can look at implementing very highly efficient heat recovery systems in labs. And these are techniques that we deploy for all of our deep energy retrofits that we're planning, to try and have as much demand control ventilation to use the least amount of energy to supply the highest quality environment we can, and then also to try and find the ways to most efficiently recover all the losses. So it is a challenge with labs, but we're launching our first deep energy retrofit in the next month or so, and that is going to be for a lab building. So we're optimistic that we're going to hit our 43% EUI reduction in this first lab building, and also have probably 75 to 80% reduction in carbon intensity. So if we're able to achieve that, that would be, I would say, a good starting point to launch our deep energy retrofit program. So going back to this here, one of the key considerations is trying to balance carbon with cost. So we could address our carbon issue by switching to electricity, because electricity is 6 times cleaner than natural gas. However, electricity costs are approximately 11 times more expensive on an equivalent energy basis. So if you're comparing equivalent kilowatt hours head to head with natural gas and electricity, this is quite an obstacle to overcome. And that this gap between the cost here of these different energy forms, we refer to this typically as a spark spread. If we are looking to electrify with a heat pump, you typically hope that your heat pump coefficient of performance, or COP, is larger than your spark spread. But unfortunately here, when you have an 11 times gap, some of the top COPs for heat pumps, are kind of in the 3 to 4.5 or 5 range. So it's still far from overcoming that spark spread. So you need to sort of take a two-pronged approach here to simultaneously reduce the need for heating, but also find a way to close that gap if you can. One of the techniques we have here in Ontario, which is very unique, we have an environment here where we have 2 rate classes. It can be a Class A customer or a Class B customer. On our bills in Ontario, about 70% of the electrical bill charge is related to a thing called global adjustment. In Class B, this is charged as sort of an energy rate rider, if you will, where that global adjustment cost, that 70%, is tied directly to your cost per kilowatt hour. Whereas if you go to Class A, that global adjustment cost is actually decoupled from energy and becomes a charge that is purely based on your coincident peak with the Ontario grid. Getting into the details is a little bit complicated, but I think that the benefit here of being a Class A customer is that it allows you to manage your global adjustment cost, which represents 70% of your bill, independently of energy consumption. So that is a big thing that we see as an opportunity moving forward. Why? Because it actually inverses the spark spread, meaning that the cost of electricity, which was 11 times more than natural gas, actually becomes close to half the cost of natural gas. When you factor in the overall efficiency of a natural gas consuming system, and you factor in the carbon tax, which is now going to be escalated up to $170 per metric ton by 2030, you really start to move this in a favorable direction for electrification, especially when you're considering things that have a very high efficiency like heat pumps. And of course, the other big impact on sustainability is the spread in emissions. So this shifts us to look at ways of managing that global adjustment cost, and that gets managed through trying to manage your peak demand. So we're trying to deploy at U of T here a strategy around managing our coincident peak demand, and this involves a lot of really interesting techniques. So it could be peak clipping, it could be load shifting, it could be just being very strategic with how we manage our growth. And these things will allow us to have a few different options or tools in our belt to try and manage that 70% cost of our bill and look at trying to bring that global adjustment cost down, because that's key for us to try and move forward with our strategy to electrify our campus. Another piece here when we're talking about the peak of the pyramid is if we're able to make changes at the peak.
Mark, there was one other question, Mark.
Sure.
The question was, do you monitor the peak pricing and load shed in the heat of the summer?
To date, no. But moving forward, if we plan to implement a strategy towards electrification, I think this will be a key component of our strategy, is to try and monitor the peaks and have a number of strategies to try and mitigate the impacts of our coincident peak. We're going to try as best we can over the next few years to try and put in a very aggressive demand response strategy to try and reduce that peak. So it's going to be a key part of bridging the gap for the existing spark spread that we have today. So going back to this, we have a district heating system, and it feeds not only U of T owned buildings, but also 5% of that heat energy goes to external clients, and 7% goes to federated colleges. But the GHG emissions sort of show up on our scope 1. So, you know, we can take two approaches to this. We can go to them and ask them to reduce their consumption. We can ask them to implement deep energy retrofits and sort of do demand side stuff, or by affecting change at our central plant level, the top of the pyramid, of course. If we do a fuel switch there, or we start to, burn renewable natural gas or biofuels, we can then definitely impact our consumers as well, including the federated colleges and our external third-party clients. Here's a wedge graph here, sort of showing our low carbon action plan from now to 2024. Some of the projects we're looking to implement and how we're looking to achieve a 44,000 ton reduction by 2024. A couple of the pieces I'd like to highlight here are our new performance standards for new construction as well as major renovations. We feel this is going to have a really good impact on our emissions over the next 5 years, and this will serve to reduce about 8,800 metric tons. We're also looking to double the solar on our campus, which is going to have a good impact as well. And even things like the lighting retrofits and building optimization, will all have significant impacts. And we're also showing here about our first steps towards electrifying our campus via heating systems with a geo exchange in King's College Circle, and also Robert Street Field, actually. So looking at our carbon neutral sort of objectives here, we went into this planning and the strategizing around this with 3 buckets or 3 main objectives. First being for renewal, and then sustainability, and also growth. So the existing campus utility infrastructure is aged and requires renewal to support the university and its pursuit of academic and research excellence. In terms of growth, we're planning significant new campus growth, and it will require expansion of the utility systems and infrastructure. And this will impact, obviously, reliability, redundancy, and resiliency. And also, we want to commit to a net positive climate impact when it comes to greenhouse gas emissions by 2050. And this will definitely require transformational changes to our district infrastructure. This is sort of what we envision in terms of our long-term strategy. So we'd like to go from where we are today at St. George. At the tri-campus level, we're at about 114,000 tons, but for just St. George, we're roughly 88. We'd like to bring this down to under 55,000 tons by 2030. And if we can, we'd even like to bring this down steeper and come down more aggressively. but of course trying to get to carbon neutrality or beyond prior to 2050. As we were planning out our district infrastructure and our carbon neutral master plan, we looked at a lot of different scenarios here for global warming and climate change and how it's going to impact our planning and our sizing of our district systems. So you can see here we have the RCP 8.5 model, the RCP 6 model, and the RCP 4.5. This refers to, the 8.5 refers to 8.5 watts per square meter across the planet as the impact of global warming with this model. So in here you sort of have your 2 degrees C sort of climate change impact. So we took this into account for sizing and developing a strategy around renewing and greening our campus infrastructure. This is that same RCP 8.5 model and sort of shows the temperatures that are forecasted in Toronto. I believe this is for 2046. So where you see the red, that's the warmer climate, that's the impact of climate change, versus the blue being our temperature now. So some of these show the impact: annual heating consumption, 0.6%, heating demand, cooling, and peak cooling demand. Is that another question that's come up there, Jamie?
Yeah, it sure is.
Perfect. I love questions.
It says, today there was a conference on decarbonizing buildings from MIT. It was very interesting. It seems no one alone can make things change.
Yeah, I would tend to agree with that. They're doing a lot of good things down in Cambridge as well, both at Harvard, at Boston University, at MIT. I think that universities as a whole represent a very significant percentage of building owners in North America. I think between federal governments, the next one is actually universities. So, being that this is so near and dear to our core missions, I think that we have a responsibility to be leaders in this space and show how we can lead the charge against climate change by trying to reduce our GHG emissions, definitely scopes 1 and 2 as quickly as we can. So I would tend to agree with what they said at MIT. I unfortunately didn't catch that lecture, but would definitely agree with them that this is a daunting task and we have to do it together. This slide here shows us sort of our current and planned developments from 2020 through to 2050. And I think this is both one of the biggest challenges as well as one of the biggest opportunities in front of the University of Toronto. I don't know where we stand in terms of other universities in North America, in terms of plans for growth and development, but we're going to be, we have some very aggressive growth planned, and we're getting close to doubling our campus, which, as I mentioned at the very start, is already one of the largest campuses in North America by student population, but we'll be doubling our square footage as well from now until 2050. I think that this renewal provides a great opportunity for us to build back better and to also help dilute some of the impact of our existing building stock that will be simultaneously, as I explained, trying to reduce the energy use intensity of those buildings. It's just a quick chart showing some of the different ages of or the current and planned developments and how they'll be phased over time. Was there another question there, Jamie?
Sure was. And it says, it's more of a comment, I guess. It says, I think everyone can share experiences and resources to make all this work as a norm.
Absolutely, totally agree. And I've got a couple slides that speak to that closer to the end, I believe. But I think that collaboration and partnerships are definitely key to achieving our goals here. This is just a quick slide I won't spend much time on. It just shows that our existing demand on electricity, is at 50 megawatts. As a bit of a side note, I believe we're Toronto Hydro's largest customer. And if we want to go into an electric boiler option, that would push our peak up to 162 megawatts. And if we're able to leverage the greater efficiency of heat pumps, that would push our peak up to 114 megawatts. This just shows some of the planning around our peak loads and what scenarios were considered moving into 2050. Was there another question there again?
Yes, it was. It says, Marc, do you think that the growth scenario will be impacted by the COVID-inspired movement to more online learning?
That's a really great question. So I hope so. Personally, I do hope so. I think that we're looking at energy use intensity, or we're looking at GHG sort of intensity of our campuses. But one thing that is going to be a big factor moving forward is space use intensity. If we have more people that have shifted to online learning, and we have less need to drive development and growth and more space use, that just like trying to save energy rather than build new infrastructure to deliver more energy, if we can reduce the amount of space that we need, that's the easy win, I think. So one of the silver linings, I think, with the pandemic is that it's really ushered us into a new era of working and learning. So I hope that does have a very positive impact moving forward on the amount of space that we need going forward, and our GHG consumption or emissions, and how we're able to impact that. So I'm very hopeful. And this, the plan that I'm sharing with you guys here too was developed pre-pandemic. So we haven't gone into how the pandemic and online learning would influence or impact these plans. That hasn't been an exercise that we've had time to tackle since the pandemic hit.
We have another COVID-related question from Al. It says, how has COVID affected your efforts? More specifically, has it revealed any opportunities for GHG reductions?
That's a very interesting question. So I think that in terms of impacting our efforts, I think it's been a distraction. So I think that we were lucky to have started this exercise pre-pandemic, and also pre my joining the University of Toronto. But I think we're lucky to have been able to see this through to completion before the pandemic really hit in full force. But I would say in terms of facilities and operations at U of T, it's kind of been all hands on deck to deal with COVID-19 related issues and keeping the campus environment safe, first and foremost. You would think that the GHG emissions and energy consumption would go down dramatically, but it sort of has a balancing impact where there's less people on site, but you still have to keep the buildings warm, you still have to operate them. And unfortunately, without having that population of 100,000 people on our campus, those 100,000 people generate heat themselves. And with them not there, you have to supplement that with dirty heat from our central plant currently. So that, although they're using less electricity and there's less activity on the campus, we're having to heat our buildings more. We might have to cool them a little bit less in the summer, but the real GHG intensive process is the wintertime heating. So COVID's had a negative impact on that for us, I would say. But overall, it sort of has balanced out to be status quo.
I think,
oh,
sorry, Marc, we still have one more question. It says, are there any existing organizational sustainability standards / guidelines that are helpful to estimate GHG emissions of organizations?
To estimate GHG emissions of organizations. I think that this really just boils down to completing your own inventories and following protocols and guidelines that are sort of established internationally, and have to go through the reporting process. I'm not sure if that answers the question, but I'm happy to pick it up again if someone likes to rephrase that. So I sort of touched earlier on the Toronto Green Standard and how the university has developed its own internal sort of adoption of the Toronto Green Standard with our energy performance standard. So the Toronto Green Standard is meant to look at air quality, energy, GHG and resiliency, water quality, quantity and efficiency, ecology, as well as solid waste. So what we did at the university, because the TGS is sort of focused on residential, multi-residential, commercial, retail type buildings, those types of archetypes, we looked at trying to find a way that we could develop and adapt the Toronto Green Standard to the University of Toronto with our specific needs and archetypes that we have on our campus. So we looked at creating a version that was tailored to residences, libraries, offices, classrooms, labs, and that we could apply that directly. And that sort of formed the basis for our new standard that was published in July 2020. But it was inspired very strongly by the Toronto Green Standard, and also to show support as, you know, as I said earlier, we're one of the largest emitters within the city of Toronto, and also one of the largest consumers within Toronto Hydro. So this was our way of stepping up and trying to create a very strict and performance standard for anything that's going to happen on our campus. This is a quick graph I borrowed from the City of Toronto showing their projected emissions for business as usual versus the impacts of the TGS. And this is just a quick snapshot of their zero emissions building framework. So they're within the TGS, they're measuring energy use intensity, thermal demand intensity, and GHG intensity, and setting targets or budgets for all these separate items. And we're doing the same thing with our energy performance standard at U of T. And of course, this is just a fun sort of picture that shows that having buildings with that are highly efficient, high efficiency systems, and increase the air tightness and the envelope integrity, you can really get a building that performs a lot better. This is the sort of tiered ratings or compliance levels that you have within the TGS. So for right now, we're still in version 3. So our standard, which mimics the Toronto Green Standard, sort of is an equivalent of multiple different tiers. There's elements of our standard that are very stringent, that are more of a tier 3 level, and there's some elements of our standard at U of T that are more of a tier 1 level. But when you take the whole standard overall and you sort of look at it, we sort of see it as being like a tier 2.7 is what I'm told we've come up with. So meeting our U of T standards internally would sort of translate in some way, shape, or form to roughly tier 2 plus for the Toronto Green Standard. So we're trying to stay a couple steps ahead of the game, and ours, much as the Toronto Green Standard does, it gets more aggressive over time. So this shows that what is tier 1 in 2018 becomes, or what was tier 2 becomes a tier 1, tier 2 here becomes a tier 1 in 2026. So as time goes on, the standard is getting much more stringent, and our U of T standard does the same thing. So as we get towards 2030 or prior, because we're, like I said, we're trying to stay a little bit ahead of the TGS, we're basically getting towards net zero energy buildings prior to 2030 as a minimum requirement. I think there was another question. We can pause and take that if you like, Jamie.
Yep. It says, please comment on U of T's plans please comment on U of Toronto plans reliance on the use of air/ground heat pumps.
Well, the timing of that question is fantastic, actually. So we're just going to get into that here on what our strategy looks like and what a net zero carbon campus looks like for us moving forward. But I will say, I'll give you a spoiler alert here that air source and ground source heat pumps are going to play a very critical role. So here we go. So we did a technology review at the very start. Looked at things like biomass, deep well geothermal, looked at micronuclear, looked at hydrogen fuel cells, looked at all kinds of stuff. What we came up with here was being able to sort of look at what kind of mix would be right for us. Anything from the conventional all the way to, on your right here, you have sort of like the all electric and everything in between. So the strategies that were shortlisted for the St. George campus were these three alternatives, where you had one which was an interconnected nodal, where you have a central plant and you have some smaller sort of central plants, nodal plants, and they're all sort of interconnected. You had another one that was more of a nodal focus, where you have your node and you have some standalones as well. And three was more of a distributed generation, where you have more decentralized options. We have a lot of air source heat pumps, you have your central plant, you have some nodes, you kind of have a bit of a mix. So we went into this and we tried to evaluate each of the different options. And here's the criteria and the weighting that we looked at for these systems. So the five categories that we looked at were environmental, resiliency, operational, social, and economic. And this is the weighting here, and so this is sort of how the options played out for us. And the option that ended up being the front runner for us was alternative one. And whoops, you can see alternative one was the interconnected nodal with the central plant. And when we look at alternative one here on an equivalent carbon emissions sort of basis, you see that this green line represents what we feel can be offset by a U of T owned utility scale solar farm, and the emissions that would be produced at 2050 with the strategic plan. So we're going to look at some project highlights here within that sort of master plan. We are currently, if you've been on our campus over the last few months, you've probably seen that we have drilling rigs that are currently digging and drilling boreholes in King's College Circle in our front campus. So we're very excited to be presently drilling Canada's largest low carbon geo-exchange system. I think that on a tri-campus level, with the projects that are currently under construction and the ones that have been done in the past, I think we're approaching 3,000 tons of geo-exchange capacity at U of T. This is a good example here where the artist has tried to depict how we're going to try and bring the geo-exchange system, bring heat pumps and this technology out of the closet and kind of make it more demonstrable and bring it sort of front row center so people can see it. Part of our landmark project here, I think, is to put underground parking under King's College Circle and to get rid of any sort of vehicle traffic in King's College Circle. So as you go into the underground parking, there's actually going to be a viewing area, we hope, where people can walk by and see the nodal plant and the geo-exchange system in operation. Here's a shot of the drilling rigs that are there throughout this winter. And this just shows you again, King's College Circle. We're going to have a nodal plant installed. I believe it's going to be in the medical sciences building, and it's going to feed these buildings that are highlighted in red. And this project is estimated at this point to be helping us reduce 15,000 metric tons of carbon per year. Coupled with the projects on the two other campuses, we're looking at over 16,000 tons. This is just a glimpse of the interconnected nodal plants. So this one would represent our central plant, and we have multiple different nodes that will be placed around campus that will be interconnected. And what we're trying to do here is work towards eliminating steam over the longer term. We're trying to also renew our central plant with low carbon or electric technology. We're looking to sort of create some resiliency with our microgrid by not having just one sort of entrance to our microgrid, but having multiple different entrance points. We're looking to, like I said, mitigate that carbon with our new construction and our renovations, and also supplement this with our offsite solar farm. So when we look now at, we talked about this previously with the deep energy retrofits, but now from a district scale, it has a bit of a different purview. So we're definitely looking to increase the efficiency of our central plant as well as our distribution. And again, the big challenge here is that we have a district system that is certainly aged and getting on in years. I've heard someone say that we have one of Canada's oldest district energy systems. It's over 100 years old, and it still currently feeds more than 80% of our heating and 20% of our electricity on our campus. I know this is probably very small for most of you, but what's in blue is steam, what's in red is high temperature hot water, and what's in green is sort of decentralized heating systems. So we're looking to modernize this and transform it with the internodal approach, where we have our central plant and have multiple different nodes that will be connected. And most of those nodes would also be tied to a geo-exchange system. We're also looking to double our solar and renewable content on campus. So although it doesn't have a massive impact on our GHG emissions, it does show our commitment towards renewable energy and doing as much as we can on our physical campus. Some of the immediate opportunities that we're looking at here are opportunities around maybe trying to accelerate our commitment and our GHG reduction. So we're looking at opportunities that are top of the pyramid that will have impacts that will trickle down to all of the buildings. Given that our existing central steam plant, as I mentioned, feeds 80% of our campus heating currently, any changes that we make at our central plant level will have that cascading trickle-down effect to 80% of our heating system. So one of the initiatives that we're trying to launch this year is a project to electrify the vast majority of the heating that's being produced at our central plant, leveraging sort of a Class A tariff, which would inverse our spark spread and hopefully make it favorable for us to do a two-pronged approach, one where we would provide electric steam using our existing infrastructure and making it sort of a relatively small change to our overall campus district system, and couple that with a robust strategy around demand response and trying to mitigate the impacts of our coincident peaks and reduce our global adjustment charges. So we hope this will have an impact of reducing our on-site emissions by 50% with just one project. So with our 2030 goal of being 37%, we're hoping this will, like I said, accelerate our commitment and our carbon reduction by bringing us to 50% reduction by about 2024. We're also looking at doing some other interesting projects. We have our St. George Academic Wood Tower. And this will be a very interesting thing, but we're also looking here at some of the embedded carbon and the advantages of mass timber. So this will bring our GHG intensity of this proposed project down to around 14 to 15 kilograms per square meter versus our target of 32. Another project is our St. George Spadina Sussex residence. This one, I believe, has a target of about 6 kilograms per square meter. So, we're going to be our lowest carbon emitting residence on our campus for sure. And when we look not at just the next 4 years, like the previous graph, which was sort of just showing this piece, when we look overall towards 2050 and beyond even, here's sort of a snapshot of what our pathway towards carbon neutrality or even climate positive would look like. We have the impact of our new design standards for new construction as well as major renovations and minor renovations. We have some of the retrofits that we're going to do. We have the geo-exchange fields. We have the electrification of our district systems. We have the offsite renewables, which will be sort of that last up to 20%. And yeah, so we're projecting our emissions to really go down, and this is our pathway to achieve that. I thought maybe I'd stop it here for a minute to see if you have any questions. The last section is sort of just a plug for our St. George Sustainability Office.
Yeah, the only question I see here is how is reduced consumption represented on the graph?
So the impact of electrifying our central plant and also electrifying through the nodal plant approach and the geo-exchange does have an efficiency sort of play on it. So our existing district system is about 83% efficient. So if we made a switch over to an electric boiler, the electric boiler is essentially 99.5% efficient. So we are getting an efficiency play there. But as I said, we're looking at also reducing the EUI of the campus by 2050. We're going to go from that 1.68 gigajoules per square meter and try and bring the overall down to under 0.7. And that's now has a mix of roughly 60% existing buildings and 40% new construction by 2050. So right now, if we didn't do anything, and even if we still met some of our standards, we would still be increasing our emissions quite substantially. The reduction in EUI is reflected in the forecasted demand that we had for our campus. So when we were looking at going from 50 megawatts as a campus going up to 160 plus, that 160 is already being mitigated through EUI reduction from our existing buildings as well as from our new construction standard.
There's also another question that says, there are steam uses for some applications. Would these use local steam generators?
Yeah, so as we're looking to convert buildings to low temperature hot water, we're trying to get them off of steam gradually. So each building or each lab, for example, that we go through and we do a deep energy retrofit, we're trying to, as a priority, trying to convert these buildings from either steam or high temperature hot water and convert them towards low temperature hot water heating. The low temperature hot water heating kind of is your gateway towards renewable technologies, such as heat pumps or solar thermal or others. Whereas the steam can tend to handcuff you a little bit. Whereas the low temperature hot water, if you want to do it with fossil fuels or with renewable natural gas or biofuels, you can do that. But you have an option to move away from combustion completely, which is part of our target. It's not an official target, but it's a preferred method for us. As we look at process steam, for things like humidification and everything, we're going to look to move away from any steam humidification. For processes like sterilization or other kinds of process steam, we're going to try and do that locally and do it with electric boilers.
Okay.
Here in a few more ticks.
Yeah. So Al's asking, can you expand a bit on the offsite renewable energy? Is this mostly electrical offsets, for example, solar or wind to offset GHG on campus?
It is, yes. So right now in our plan, we have an offsite solar farm, and we're looking to use this as a U of T owned asset. to do virtual net metering and offset the emissions from our St. George campus.
Excellent. One question is, I saw Wahlberg on your map. I'm guessing that was the building. Is there a time frame for the transition?
Time frame for the transition. I'm not sure where we would have had Wahlberg in here. I'm going to go back and take a quick peek here. I think this is probably where the person saw Wahlberg. So the transition, I don't know what the exact date for that transition is, but from a building occupant point of view, when we're transitioning from the existing system towards the geo-exchange system. Yeah, good question, actually. I don't know.
Excellent.
Because Wahlberg may actually require a steam to hot water conversion in that building. So.
Okay, so there's another question here. It says, can you comment on how hot water versus steam can get us to a lower GHG profile?
Yeah, definitely. So I think building on what I said before, where sort of going towards low temperature hot water is a gateway towards reusing more renewables, and specifically heat pumps. You know, heat pumps are some of the most efficient means of generating heat, but they're not particularly good or efficient at generating very high temperature heat. So, you know, there are some systems like a York CYK that can get into the 160, 170, 180 Fahrenheit. But generally speaking, most heat pumps that aren't cascading are really kind of limited to practically about 140 Fahrenheit or 60 C. So if you can keep your heating temperatures below that amount, you can really leverage the added efficiency of heat pumps. So whether this is air source or whether it's ground source or water source, it sort of leaves the door open for you to use heat pumps and leverage that sort of 350% efficiency versus, you know, maybe a combustion system, which would be less than 100%. So you're kind of getting a threefold or better gain in efficiency by leveraging the refrigeration cycle and the inherent advantages there of the phase change. So that's definitely sort of part of our core strategy here, is to try and find a way that we can decouple the global adjustment cost, which is 70% of our electricity cost, away from the actual consumption of kilowatt hours, and then to leverage that low cost of the kilowatt hour and the inverse spark spread to power our highly efficient heat pumps in a cost-effective manner where we can reduce the emissions sixfold as well. And also when you know, generally speaking, when you look at lower temperature at a district level, you can really also mitigate your distribution losses when you have a lower temperature. So you have less radiant and conductive losses through your distribution piping. And you know, when you have steam, you also have to deal with steam traps and steam leaks and things like that, where you'll end up having less leaks and less losses in your entire system when you move to low temperature.
Excellent. Just following up, I think, on the Wahlberg question. The question is likely 5 to 10 years, question mark?
You caught me. I really don't know. I would say that it's not on my immediate horizon for deep energy retrofits. So it's probably at least 5 years out.
All right, we'll do this one more question here before we wrap up the presentation, which is, based on some of my readings, Scope 3 GHG emissions of organizations are normally found to be higher than Scope 2 and Scope 1 GHG emissions because of too much material consumption and travel. I am just curious to know, how does U of T stand in this space?
Well, I think we've done stellar in this past 12 months in terms of our travel emissions. Joking aside, we haven't taken a really strong look at Scope 3 at this point. Our strategy is really focused around Scope 1 and 2. And we are looking at implementing and piloting sort of programs that will impact Scope 3. But, you know, I think that we're not quite there. That's going to be a next step for us.
Well, that is also all the questions. So I think it's time to press on.
Perfect. So the next step here is really just looking at partnership and engagements. We are proud to be part of the Mayor's Greenville initiative with the City of Toronto. As I said, we are a very large consumer and an important sort of stakeholder within the City of Toronto. So we also want to be part of playing a leadership role in achieving the city's targets as well as our own personal targets. We're also a member of the University Climate Change Coalition. So we joined the coalition in 2018. There's over 22 universities in North America that have committed to reducing GHGs in their campuses and also in our communities. Our low carbon action plan is a response from university operations to achieve our commitment on climate change, climate action. And we're also a member of the U7 Alliance. So U7 Alliance is represented by over 45 universities worldwide. And again, we're rallying around our commitment towards carbon reduction and climate change. And we're there to try and engage our local stakeholders and internal stakeholders and play a leadership role in the fight against climate change. So these are just some quick facts about our sustainability office here at St. George. We manage 5.5 billion in physical assets, over 130 buildings, over 14 million square feet. We have 150 buildings served by our district system. We produce 80% of heating and 25% electricity. And through our energy conservation program, we've saved 19 million in utility costs since 2011. I would say that we have very, very strong leadership here at U of T. I've been with the U of T for 7 months, and prior to this, I was working with a lot of different institutions in North America. And of the dozens and dozens that I worked with in North America, including some very prominent universities, I would say that I feel that we have the strongest commitment from the top down, not only in terms of pledges or commitments, but actually funding and supporting projects and transformational change, which for me is extremely encouraging. I would definitely applaud our leadership here for being very, very strong and bold leaders. When we look also at some of the other impacts we've had from the sustainability office, there's close to 500 tons of paper recycled in 27-18. Looking at converting LED light bulbs, we're currently we're supposed to get bids, I think, this week for a conversion. We're spending another $700,000 converting light bulbs over to LED, and hope to have a phase 2 of that they'll follow it up before June this year as well. We're aggressively trying to save water. Water is another key part of our performance standard, where we're looking to reduce water consumption by over 50% versus a LEED silver baseline. We have some LEED silver and or sort of LEED sort of certified buildings. But also as part of our performance standard, we require every minor renovation or major renovation and new construction project to shadow LEED silver certification. So although we don't necessarily pursue the actual certification on every project here is being built to a minimum sort of LEED silver criteria. And that's all I've got for you today. So if there's any other questions, I'm happy to take a few more minutes to answer them.
Yeah, thank you very much, Marc. I'll pop on my camera now. Yeah, thanks a lot, Marc. I think that was very interesting, and it's definitely looks like a really big project to get this plan going. So there is a question in the chat says, are you taking advantage of government incentives?
Wherever we can, absolutely. I think that the government is a key stakeholder, and they're trying to. Yeah, we're supporting the provincial government, the municipal.
The button at the top right-hand corner. Yeah, that one. There you go.
Oh, great. Thank you, Jamie.
No problem. Sorry, continue.
So we're supporting all three levels of government, and being the size that we are at U of T and our ability to affect change on a larger scale, I think makes it attractive for both the municipal, provincial, and federal governments to see us as an ally in trying to achieve their goals. And with our commitments and our plan that we have in place here that we're trying to deploy, we're definitely looking for opportunities for grants or funding to try and accelerate our plans.
Excellent. Next question is, are you collaborating with U of T Civil Engineering and Toronto Atmospheric Fund on lessons learned with building retrofits?
Definitely. So I see the TAF as being an excellent resource locally, and I look forward to collaborating with them and sharing lessons learned. Part of the Mayor's RENEWAL initiative is that we do participate in roundtable sessions and forums with other universities as well as other members of the RENEWAL to share lessons learned and best practices, and also share activities and initiatives that we're taking on. So I think that in terms of partnerships and sharing learnings and best practices, that's really a key piece. I mean, someone mentioned earlier that we can't do this alone. I think that was a comment from the MIT lecture, but it's absolutely right. I think that our role in higher ed, if we're going to be effective, we have to try new technologies, try and be leaders, be in the forefront, and be implementing and pushing the envelope, and also sharing best practices with everyone else, and serving as an example, right, to show what can be done.
I agree with that, that's for sure. I don't see any other questions. If anyone has a question, please put in the chat, or maybe we'll wrap up. It's already quite late. So let's actually begin wrapping.
The last piece that Jamie was asking if we're collaborating with the Faculty of Engineering. You know, and I want to thank you for inviting us to come and speak. I think this is, with me being new at the U of T, this is sort of a first step for me to start collaborating with Jamie and your team at the Faculty of Engineering. And like I said, any chance we have to integrate staff, students, and faculty with our projects, we really want to jump at that. We think that's a core piece and a core way that we can support the mission at U of T.
Sounds like a good plan to me. Anyways, so thank you everybody for coming, and thank you, Marc, for the great presentation. And have yourself a good evening. Thanks again for coming. Okay, goodbye, everybody.
Thank you very much.